This work would not be possible without my excellent collaborators, Lance, Stan, and Yeongjin. We're all from Oregon State University. So this talk is about public key authentication in SSH, so I'm going to start by just describing how that works. So when you connect to a server with SSH, your client says, hey, here's a public key. Do you want me to authenticate under this public key? And the server might say no. And so the client software will pick another public key and offer it to the server, and maybe the server says no again. And eventually, we hope that the server will say yes to one of these advertisements. And at that point, the client can sign a nonce and authenticate under that public key. So that's the basic setup for public key authentication in SSH. And one thing you might have noticed is that the server can just say no to every single advertisement. And if it says no, then it's going to learn all of the keys that the client is willing to offer. And of course, this can be used to fingerprint the client. So I first learned about this problem from a blog post by Filippo Valsorda, and he encouraged the readers of his blog to SSH to this server that he set up. And so I did that. And when I do that, this is what it looks like to me. And in particular, his SSH server knows my name, and it knows my GitHub ID. And so how does it know this? Well, there's two reasons. First is that the public keys that you upload to GitHub are truly public. It's really easy to just go to GitHub and view anybody's public key. And second, the SSH client by default is willing to send all of the public keys that it knows about to any server that's willing to refuse all of the advertisements. Okay, so that's kind of interesting and creepy. I'll point out that you can configure your SSH client to only send the keys to the servers that you expect. So if this were the only problem with SSH authentication, I wouldn't have much to talk about today. But there are some other problems with SSH authentication that we can improve, and that's our goal in this work. So another problem, just switching things around a bit, is that the client can offer somebody else's public key. So the client can offer a key for which it doesn't know the secret key. And then it can observe whether the server is happy with that key or not. So the client can kind of probe the server to see whether it is familiar with a certain public key. It's possible in principle that you can avoid this in the SSH protocol. In principle, the server could demand the client to send a signature along with its advertisement to prove that it really knows the secret key. As far as we know, there's no SSH implementations that actually expose this as a feature because none of the SSH clients that we know of actually would do this. But that's technically possible to fix without making drastic modifications to the SSH protocol. But there's more issues here. One issue is that the server sees exactly which key was used to authenticate. And what's more, the server has a signature under that key, which is like proof that it can show to somebody else that a particular key owner authenticated to the server. This is pretty fundamental to the SSH protocol. This can't be fixed with simple configuration fixes. And as we'll see in this talk, it is possible to authenticate without letting the server learn this kind of information. And finally, it's not only bad when the server says no to every request. If the server can just say yes to every request, that's also kind of bad because the server can act as a honeypot. So imagine that the client connects to the wrong server, but decides to trust that server because it's the first use. That's a common scenario. So in this case, the client would be mistaken about which server it's connected to. And so this is another problem that our new approach can improve. So we can't completely protect a client who trusts the wrong server on first use, but we can make things harder for a server in those cases. So the goals of our work are to design a new authentication method for SSH public keys in which the server and client learn minimal information about each other. If I could convince the entire world to generate new key pairs so they can use my fancy cryptography, well, my life would be a lot easier. But the problem is, well, it's not a problem. The truth of the matter is people have SSH keys already, and they're quite happy with those SSH keys. And those keys are a mixture of RSA keys and ECDSA, EdDSA keys. So we want to design a mechanism that's compatible with these existing key pairs. It's not realistic to imagine that the entire world is going to generate new SSH keys. And finally, we want to minimize the reliance on configuration. So we want things to be kind of safe out of the box without relying on special configurations. So, power users like us can probably handle, configuring our SSH clients, but these configurations can be, error-prone for novice users. Okay. So what we do in this work is we design a new authentication method, and I'll give you an overview of the guarantees that it provides. So the client has a set of secret keys that it knows, and the server has a set of public keys that it considers to be authorized. And these can be a mixture of different flavors of RSA keys in a single interaction. And so in the notation here, I'm imagining that SK1 is the key that goes with PK1, and SK4 is the key that goes with PK4. So what does the server learn from our protocol? Well, the server learns the number of keys that the client has, and the server learns basically a single bit. Does the client have any of the secret keys corresponding to these public keys? Yes or no? But it doesn't learn which one the client has. The client learns how many keys the server holds, and the client also learns which ones are authorized. But what's important here is that, for example, the client can't learn whether public key number 2 is authorized by the server because the client doesn't have the secret key for public key number 2. Our method doesn't really depend on any special configurations. It just works out of the box. So it's safe to use any of your keys in any authentication attempt. So that's kind of nice. And one thing that's kind of subtle is that a server who's trying to act as a honeypot can't convince the client that they've connected unless that server explicitly knows and explicitly includes that client's public key in this protocol. So there's no way for the server to just say yes and let everybody in. The server has to know your public key if it wants to let you in. So that kind of makes it harder for a server to intercept your connection on a first use. So given the limited amount of time we have, I'm not going to say too much about the techniques here, but I'll just give the big picture of how our protocol works and the main tools that we use. So in our protocol, again, the client needs a set of secret keys. The server needs a set of public keys. And there are two basic building blocks to our protocol. The first one is what we call an anonymous multi-chem. So just think of this as a public key encryption. So the server is going to generate a ciphertext C that's addressed to a set of recipient public keys. Okay? And the different secret keys will decrypt this ciphertext to different plain text. So when the server generates the ciphertext, it knows that public key number 1 is going to decrypt this ciphertext to plain text number 1. So those are these MJ values that the server learns. And finally, this ciphertext is anonymous, and that means that the ciphertext doesn't leak anything about the set of recipient public keys, except maybe it leaks the number of those public keys, but it doesn't reveal the identities of the recipients. So the server generates the ciphertext, sends it to the client, and now the client holds a set of secret keys. It can decrypt this ciphertext many times under each of its secret keys, and it gets a collection of plain text. Okay? If any of the client's secret keys match the public keys of the server, then these two parties are going to have some plain text in common. So that's the main idea of this next step, where we use private set intersection. So the parties can test whether they have any items in common. So in private set intersection, each party has a set of items. In this case, it's these plain texts. And we're going to use a variant of PSI where the client learns the entire contents of the intersection. So the client learns which of its keys basically were successful. And the server just learns whether the intersection was empty or not. Okay, so we need a special variant of PSI with those properties. So in our paper, we show how to build these two building blocks, obviously. I guess the novelty of this first step is that most work in the crypto literature just assumes that everybody has the same flavor of key. So it's not difficult, but we show that we have to show how to build one chem object that works with a mixture of different public keys. And it's not too hard for RSA, but for ECDSA and EdDSA, we had to, those are signing keys. Those are not usually used for encryption. We're sort of asking the users to use their signing keys for encryption. And so we had to be careful that that works out. So you can see the paper if you're interested in that kind of a question. The leading private set intersection protocol for sets of small sizes like this is a one from last year from myself and Ni Triu. And we had to extend that protocol to support this proof of non-empty intersection. So we needed this feature where the client can prove to the server that the intersection was non-empty. That's not something that I'd seen before in PSI protocols, so we show how to do that. And finally, it's the crypto session, so I feel like I can say the word UC security, that's fine. So the security analysis is all in the UC security model, so that's kind of, if you're not familiar with what that is, that's like the gold standard for proving security of an interactive protocol like this. So if you like that sort of thing, check out the paper. So we implemented this new protocol in OpenSSH. You can see our source code at this URL that I've listed here. Like I said, our protocol supports a mixture of different flavors of keys in a single interaction. But RSA keys are much, much slower than elliptic curve signing keys, as you may know. So the worst case for us is if all of the keys in the system are RSA, and the best case for us is if all the keys in the system are ECDSA. We didn't find much difference between ECDSA and EdDSA. They're basically the same. So I'll sort of present the best and the worst case performance of our protocol here. A typical scenario is, you can imagine a client with 5 keys connecting to a server that has 10 keys. That sort of describes my experience connecting to GitHub using SSH. So our protocol is very practical for this kind of a setting. So tens of milliseconds to authenticate, a couple kilobytes to authenticate. The times here are measuring like the entire time, the wall clock time from the client, from the time you press enter until the time that it shows you the prompt. So of course, this is on like a fast network, but the amount of effort here is pretty minimal compared to network latency. A more ambitious setting might be a client with 20 keys and a server with 100 keys. So I don't have 20 keys. I don't know how many of you have 20 SSH keys on your computer. I don't know how many of you are committing to GitHub repositories that have 100 committers. Maybe some of you do. Even then, this is reasonably practical, and especially for the ECDSA keys. But even for RSA keys, it's like reasonable for what you might expect to spend for authentication. We also decided to just go crazy and imagine a scenario where the server has 1,000 keys. Okay, this is a bit slow for RSA, because doing 1,000 RSA exponentiations is a little slow. But we're not talking about weeks here, we're talking about a second. And for ECDSA keys, a quarter of a second is not too bad. Maybe another reason to switch all of your SSH keys to the new world of ECDSA keys. All right, so just to summarize, in our paper we have a new authentication protocol. It's suitable for SSH. It reveals a minimal information to both the client and the server. It supports existing flavors of SSH keys that you and the rest of the world already have generated. It's safe to use out of the box with no special configuration required, so it's kind of not fragile in that way. And you can read more about it on ePrint, and you can check out our source code. And that's my last slide. So thanks for your time, and I'm happy to take questions if we have time.